right, so if x and y are in a constant rate of change relationship, like this, where there's one rate that tells you how a change in one impacts a change in the other, the value of that m here, we said, is 2.75, meaning $2.75 per pound. For any additional number of pounds of snack mix purchased, multiply that number by 2.75, and you get the extra number of dollars that that additional weight costs you when you go to purchase your snack mix. So this doesn't give you the overall values of x and y. It doesn't tell you how many pounds altogether that you've bought or what the overall price, including the cost of the gift box, is. This relationship, this dy equals mdx, or in general, that's the general form, or in this case, it'd be the dy equals 2.75 dx. That just tells you the relationship between variations in one quantity and the other, variations in the weight and the price. When one changes by a certain amount, how much does the other change by? Not what it started and finished at. So if you remember that Canvas quiz, y final minus y initial, we wouldn't have been able to use that method here to calculate any dy because we didn't have any values of y, the cost of a gift with x pounds of mix in it. We didn't have an initial value or a final value, but we were able to calculate dy, or we would be able to calculate dy as long as we knew something about dx. So as long as I knew something about, and this question we started on Tuesday, this, where we said, oh, well, 2.75, that's the dollars per pound. So looking at this 2.75 times 1.5, if that's supposedly something related to this problem, that would be that m dx. So the additional cost you'll pay for 1.5 more pounds of trail mix is 2.75 times 1.5. dy is this 2.75 times 1.5, not by doing a subtraction, y final minus y initial, but by its relationship to x, whose change we know. If we know the amount of change in x, in this case the amount of additional snack mix purchased, and the rate at which we're charged for snack mix, $2.75 a pound, we can find dy that way as well. So a change can be computed for a single variable by final minus initial, but if you have a relationship to a second variable, if you have two quantities whose values are related in this constant rate of change way, then we can find changes in one based on changes in the other without knowing specific overall total values for either one of them. We can just compute the changes independently, which is nice. That's actually good. That way we don't have to, it doesn't depend on how much snack mix I already have, how much an extra 1.5 pounds is going to cost. It's just, oh, 1.5 pounds is going to cost me 2.75 times $1.5 more. So if I were to remove 0.4 pounds of snack mix from the bag and return it to the bin, like, ooh, this is too heavy, I didn't want quite that much, what would that change do to your costs? I don't know the overall cost because I don't know how much I have in there. I don't know values of y. I don't know values of x. But if I take out 0.4 pounds of snack mix from my bag, I can compute how that's going to affect my cost, how it's going to make the cost more or less, we hope. So what would I do to find the amount of decrease in my cost? Just 0.4 times, same scenario, 2.75, right? Whatever 0.4 times 2.75 is, that would be the value of the change in the price. What's the value of dx? So I'm missing something from that statement. What's the value of dx here? How much did my weight vary by? Yeah, it changed by 0.4 pounds, but it decreased by that much. So it would be negative 0.4. So thinking about that dy, say, oh, our price went down by, and it's perfect. If you're saying an English sentence, you say that you do this a lot. The price decreased by 0.4 times 2.75. If I want to represent the value of dy, I don't want to say 0.4 times 2.75. I need to throw in a negative someplace because it should somehow indicate that it's a decrease. dy is becoming smaller. So dx would be negative 0.4, just writing out values for these that correspond to the situation. And then dy would be negative 0.4 times 2.75. But again, if you're writing a sentence or explaining it, you don't necessarily have to use a negative number. You could say that dx, we could be talking about dx, the change in the cost, or no, the change in the weight. The weight decreased by 0.4 pounds and the cost decreased by 0.4 times 2.75. You don't have to put a negative sign in because you already said decreased. But if you're writing out just values for these, you would need to include that negative sign. So m is still the 2.75 it was before. That's nothing changed. It's the same scenario. It's a constant rate, meaning it's the same every time. So, different situation. Starting fresh, new day, new example, but just kind of wrap up this to make sure we're on the right page, and then we'll go on to something else. So a soldier lowers an American flag from the top of the pole at 0.75 meters per second. This means that during any interval of elapsed time, the height of the flag in meters will decrease by 0.75 times that amount of time, whatever it is. However many seconds go by, I can calculate the number of meters that the height decreases by during that time. So suppose I let y, just to define what symbols we should be using, if we let y be the height of the flag above the ground, measured in meters, see if you can define, well, y we've already got, but x, y, dx, dy, and m for this situation. Just define them. We don't have values for all of these, but just what would they mean? And by completely and precisely, maybe some units or what it's relative to. Notice that that y, the height of the flag above the ground, as opposed to just the height of the flag. All right, so we've got three different sorts of things that we're defining here. We've got these x and y, which are our main quantities that we're comparing or relating to one another. Dx and dy are related to x and y, so they're the same sort of thing. They each measure a change in one of the other quantities, one of the other things that we're talking about in this. And then m isn't a variable of any sort. M is standing for this constant rate. So in terms of defining these, x and y should have kind of similar sounding definitions in terms of the things that are included in them. So y, we already said, was the height of the flag above the ground in meters. So notice it says we've got this height. That's the basic thing that we can measure. We can measure a height. We need to measure a height relative to something. So like height above my head, height below a bird, like whatever it is, height above the ground normal way to measure it. Sometimes those are less defined, like if we're talking about population, you notice it, okay, so it's the population of people. That some things require kind of less definition because they're more, there are fewer options for what they could be talking about. But the height of the flag above the ground in meters. So x, number of seconds since the flag left the top. So we've got x as a time. You could say it's the time in seconds, if you wanted to word it kind of the same, since the flag left the top of the pole. We do need this sort of relative to what, because otherwise, is it time since noon? Is it time since I started reading this question? Time since when? So like time 0, when would that be talking about? Oh, well, we want it to be the time when the flag was at the top, when we started this problem. So dx and dy, though, are different sorts of things. Again, dx and dy are measuring changes in x and y. So their definitions aren't going to have this same relative to what, because they can be from any initial to any final value of the x or y. So I don't have to say since it left the top or something like that. For dx, this is an elapsed time. It's going to be measured in seconds. Some amount of time that goes by, a variation in time. There's a lot of different phrases you could use. So I could say a variation in time. We're measuring it in seconds. It has the same sorts of units as x does. But say a variation in time, a variation in elapsed time, an amount of elapsed time, something like that. But it indicates a change in time. dy, kind of similarly, is just talking about a change in the height of the flag, measured in meters. So we could word that a few different ways. We could say it's the change in height. We could say it's the variation in the height. We can say it's the difference in the height. But that difference or change or variation is going to be measured in meters. The thing, again, that I want to point out is that dx and dy don't have this relative to some starting point sort of key, because final minus initial, when we were talking about that computation, it doesn't have to be initial as in time 0. It can be any interval of time or place or whatever that you're interested in. So you can start at any point in the relationship and go to any other point that's, generally speaking, farther to the right graph-wise, but it might be later in time, it might be farther down the road, it might be, whatever the situation is. But it doesn't have to be final minus initial as in beginning initial. But m here is this constant rate of change of y to x. So the constant rate of change of the height of the flag relative to time going by. We could say it's the speed at which the flag is being lowered, this constant speed at which it's being lowered, the constant rate at which it's being lowered. There's a lot of different phrases you can use. There's not like one right set of words that you have to use or else. There are some wrong things you could say, obviously, but there's a lot of different correct ways to describe this also. So don't try to turn this into a game of what's the word that I have to say or else I'll get this question wrong. That's not what this is. Just I want to make sure that we have a variety of ideas of how to put together a correct definition of these, the things that they need to include, and in some cases the things they shouldn't include. But in any case, this m, this one, regardless of not having a specific situation in hand, we actually know its value because it's not changing. Its value is negative 0.75 and its units are meters per second. So let's look at a specific situation. Remember that m constant rate was negative 0.75 meters per second. So suppose I'm looking at this question. How much does the height vary between 4 seconds and 6.9 seconds since the flag left the top of the pole? So thinking about this, dx, dy, and m, well, m we know a value for. Think about how you could compute or what the value of dy and dx relative to this situation might be. Notice that I don't know the height of the flagpole or how high the flag was at the beginning, so I don't know any overall y value. So what about this? Let's see, between 4 seconds and 6.9 seconds. 4 and 6.9 are both values of what variable? X, right? They're not dx values, but we could find a dx value from them, indicating the elapsed time during this specific interval. So a dx that might go with this situation we could find by doing x final minus x initial, or 2.9, right? What about dy? What would be the meaning of dy for this kind of slightly more specific than the last page? The meaning of a dy in this situation? Okay, the change in height between 4 and 6.9 seconds. Okay, and how would we compute that? Yeah, take dx and multiply it by m. dy equals m dx. So if I have 2.9 seconds and m, our rate of descent, was given at negative 0.75 meters per second, we do negative 0.75 times 2.9. So 2 something meters lower and come out to be a negative result for dy, which should make sense. That would mean that our height decreased. As time increased, height decreased at a rate of 0.75 meters per second, and time went by 2.9 seconds during this example. All right, so I hope that that is not a mystery. There's a lot of things to think about just in terms of making sure you're precise about what you mean, what you say, what you write. But I hope that the concepts behind this aren't particularly challenging, like, oh, multiplication. Multiplication I hope is good. But keep in mind what we were using it for and what our variables do and don't mean that we've presented so far. So thinking of variables, I do want to talk about what it means to be a variable. Let me get this guy up here so I can maybe point at some stuff. All right. So terminology-wise, like I said, this first week we got a lot of kind of terminology and notation to iron out, make sure we're all on the same page, and when we use words, we know what they refer to with precision, so that we're not misconstruing what we mean, so that we're not confusing someone else by using a word that they use differently, just to make sure we've all got our vocabulary down right. So variables, parameters, and constants are 3 different types of things that sometimes involve symbols in math. And so lots of people just say everything that's a symbol or a letter, we'll just call it a variable. They're not all variables, because variables vary. Variables are letters or notation that take on values of something that is changing in a given situation. So in the flag situation, somebody's lowering a flag. So time's going on and the flag's getting lower, and we can talk about the relationship between those. But during that situation, time changes. Well, time kind of always changes. That's how it works. And the height of the flag changes. Lots of other things change, but those were the things we were talking about. But we've got a changing quantity, something that's value is varying, something that we measure with numbers, and we can see it either increasing or decreasing or both. If we've got a constant rate of change, it's only going to be doing one of those two, increase or decrease. But a variable also is a letter or symbol. So the quantity itself, the height, I don't say height is a variable. So y was my variable that represented height. Height's the thing that changes. Y is the variable that we were using to represent the height above the ground, measured in meters. So variables are things where it makes sense to talk about a domain. The domain is the set of all the possible or reasonable values, depending on if we're talking about some kind of abstract function where I can think about what would this variable be allowed to be, or how would it come out? What sorts of different values could it take on? Or if it's something like the flag situation, well, time since we started lowering it would only be 0 or larger, and probably not up through infinity, because it's not going to take infinity seconds for the flag to stop being lowered. And the height, well, would again be height above the ground, would again be something from 0 to, well, however tall the flagpole was, which would be not infinity. Thinking about if I were writing a linear function, I might write something that is a linear equation with a negative 0.75 slope, and those in general, x and y, can be anything. But the domain, relative to a situation, lots of time is limited by reality. So whether I'm talking about just a domain or practical domain, or just a generalized set of values that, generically speaking, could be used in the same mathematical relationship. But variables are things that have those varieties of values where you're thinking about what are all the possible values this could take on. So parameters, let me scoot this a little bit. Parameters are also symbols. We've been using one. Parameters, letter or symbol, that represents a value that stays constant within a given situation. The m that we were using in this dy equals m dx. M is not a variable there. M was taking on one value per question. So it was negative 0.75 in the flag question. When we were talking about the candy question, it was whatever that was, 2.75. So using the symbol m in place of the specific number is using a parameter. And that's useful if I want to describe dy equals m dx, just like y equals mx plus b that you learned forever ago. Like the x and the y you put in a bunch of numbers for, but in a real equation, like the m and the b were one number each. They didn't change during your equation. The m and the b in that, those are parameters. They're placeholders for a single number at a time that doesn't vary within the question. But if you do another question, you can pick a different value to use for that. And our dy equals m dx is the same way. It's the same m. That m is a placeholder for a single number that's going to remain constant while we let the other things take on a variety of values. So this parameter is a letter that stays, it's a letter representing a quantity that stays constant within a situation. But the reason that we use it is because, well, maybe we're going to talk about a bunch of different situations, and from one to the other, we're going to use a different value of m. Now, so this is what I was saying. In a new situation, the parameter could take on a different constant value. A constant in mathematics, I don't want to call m a constant. M is a parameter that we were using to represent individual constant values at a time. A constant is something that has the same value all the time, like pi is a constant. It has a symbol that goes with it. It happens to be a Greek letter, not m from our own alphabet, but other symbols like E in mathematics stands for Euler's constant. That's 2.718, the base of the natural log. Even square root of 3 that has symbols in it. It's not a letter symbol. We've got a doodad symbol over top of a 3, but that expression altogether represents one constant value. We just have some extra things that we use around that 3 that make it into some constant whose value is not 3 anymore. So these are just some examples, but a constant's a value whose value is the same all the time, and we just happen to have a symbol that we use to represent it. This is something that, with it, it's confusing for people that are learning math, that there are some symbols that have a specific numerical value or relationship attached to them. And you have to just know these, but that's what's meant by a constant. You could go look it up in a book somewhere, and there it is. There's a value for that. Or look it up on the internet, I suppose. You don't have to use books. But books would probably have them too. So in any case, so the use of the word constant, so if I say something is a constant, that's like E, or 12.7 is a constant, just a regular number symbol. Word 3 is a constant. It has one value all the time, and that symbol is how you represent what its value is. A parameter is typically, some other sort of letter. It could be something from our own alphabet. It could be a Greek symbol. It could be some other symbol. It could be little weird star things, whatever. But a parameter is something that is not look it up and find its value from some reference book. It's just a placeholder that we're using that we can assign values to later. And that's used a lot in computer programming where you just, and I'm going to define something to be a parameter, and then with individual processes, I'm going to decide what number I'm going to use for this go round. What if I put in this value? What if I try a different value? But a variable is something that represents a quantity that's changing. A parameter is something that represents a value that isn't changing within a situation. And a constant is constant all the time. So there's constant quantities and varying quantities that we can talk about in situations. And then there's this other category of things that are just called constants. So it's a little bit confusing in that sense. But let's take a look at some examples. So suppose I have a fish tank, a cylindrical enclosure or tank used for raising fish. One particular tank has a depth of 5.4 feet, a radius of lowercase r feet, and it's being filled at a rate of 17.9 gallons per minute. There's a bunch of different expressions here, 1 through 9, that are somehow related to this situation. And think about whether each one is something that's constant or varying. And then if it's a symbol, if there's a symbol in the number 1 through 9 that you're talking about, whether that symbol then qualifies it as a variable or a parameter, or if what you're looking at is just a known constant. So take a few minutes and discuss with maybe the person next to you, or people. You don't have to only pick one person. So I'm trying to get this doodad to work, and it's being stubborn. Put this over here. This guy's nice when it works, but I'm sure it's going to make that quit again. Let me just try. Yep. Where's the... All right, there we go. Get this updated or something. All right, so of 1 through 9, looking at these, we're supposed to identify, first of all, you're supposed to identify, which of these 1 through 9 represent varying quantities and which are non-varying quantities with respect to this situation. So what about number 1? Capital V, which is representing the capacity of the tank in cubic feet. Is that something that is changing or not changing here? Not changing. It's one tank. It's not going to start getting taller or wider while the fish are in it. We hope that would be pretty weird. So this would be this is a non-varying quantity. Let me see if I can get this to right. Non-varying. So let's see, what about pi? Is pi varying or non-varying? Yeah, now pi is kind of related to this because it's cylindrical. If I were going to compute some stuff, we'd have a circle in pi. So pi is non-varying. Yeah, it's non-varying all the time. What sort of thing is pi? It is a constant, a mathematical constant. It's not, I mean, you can look it up in a book. You can look it up on the internet. Let's see. Now look at number 1. Number 1, that capital V, non-varying. What sort of thing is V? Yeah, it's not a variable because it's not varying. Is it a parameter or a constant? It's a parameter. So V isn't something that I could go find a reference for online. What's the value of V? And it tells me. That's just a symbol that we made up for the purposes of this question. If we had some more information, we could find the value of it. Maybe we have enough. 5.4 feet. Nope, we don't have quite enough. We know the depth of the tank, and its radius is r. So I could write an expression for V, but it would involve r, because radius helps us find the capacity of a cylinder. So this capital V here, since that's not something I can look up in a book and find, it's not a constant, but it's a constant quantity. That makes V, this capital V, a parameter. All right, so what about number 3, 5.4, the depth of the tank in feet? Is that varying or non-varying? Non-varying. What about 5.4? Is that a constant or a parameter? It's a constant. Yeah, 5.4, it's not something you need to look up, just we have a system of numbers and that's one of them. So this is I guess, mathematical constant. But yeah, it's definitely not a varying quantity. .4 is just a constant. I'll abbreviate that. What about lowercase r, the radius of the tank in feet? Varying or not varying? Not varying, yeah. We've got a tank, it's one tank. It has one capacity, it has one radius. I don't know what they are. I could relate those two to one another, but they're not changing. So as this isn't changing in this situation, this concept is non-varying quantity, the radius of the tank, and the symbol r is a parameter, just like V was. So if I gave you a value for r to use for this problem, then you could find the corresponding value of V, since we already know the height, the depth, however you want to state that. Let's see, what about number 5, the number of fish in the tank? Changing quantity or constant quantity? Probably changing. We're kind of having a discussion about this. Maybe there's, eggs and fish being born and being bred, whatever, but there's probably definitely at some point in time there's going to be a fish that dies, at least. So we've probably got a changing number of fish in there. So this is a varying quantity. This one's a varying quantity. Oops. Is this a parameter, constant? variable? Well, there's something missing. Yeah, it's a varying quantity, but there's not a symbol. If I call it like capital N, the number of fish in the tank or something, N would be a variable, but there's not a variable here. I don't have a symbol to represent this. I'd need to make up a symbol in order for this concept in number 5 to be something I could describe as a variable. So a variable is a symbol. This is a varying quantity. So I've got a varying quantity, but it's not a variable, parameter, or a constant. There isn't a symbol for it. So there's no letter. I'll just say it that way to be brief about it. So it's not a variable, but not because it's not varying, but just because there's not a symbol given. But I could say, let f be the number of fish in the tank. Then f would be a variable. But this is just the description of a variable, or the description, it's a varying quantity that's described. I just don't have a symbol for it. Question?
Okay. I don't think it's variable.
Okay.
I think it's a parameter in the bounds of a given situation.
Okay.
Because the context is not concerning the amount of fish in the tank, but the volume, the depth, right, the radius of the tank, and the water within it.
Okay.
The given situation is purely about it's the parameters of the tank itself, right? I mean, you could, hypothetically speaking, weld parts onto the tank and make it bigger, which would make the radius of the tank
Agreed.
different, a variable, right? So within the context, it doesn't mention anything about changing the fish. I would argue that that's a parameter.
Okay. Yeah, so I guess I was thinking of it as we're having this fish tank and it's there for a while, but time isn't mentioned. You're right. So there isn't any time going by that happens, so there isn't any, however many fish there are. Just like, and yeah, so as time goes on, there could be more fish and fish die off, just as we could build more onto the tank. So fair. And that's a good description of how this situation, there's not a problem to solve with it. So if there were a problem posed, like suppose that over the next 2 months, we build the tank up, blah, 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 then the height and the capacity could be variables then. We could talk about how those change. Or if a different situation were given and it was posed as like over the next 2 months, the fish are fed and we track the number of them, then we could talk about the number of fish being a variable. So yeah, fair. I agree. So depending on additional context here, this number 5 might or might not be anything that's varying. It's not really a parameter either because, again, there's not a symbol. So it might be varying. Here, I'll change that into a question mark. But we definitely don't have a symbol for it. So the number of the fish in the tank at this point is a concept that depending on what additional, like what we're going to do with this information, this could be something that varies or doesn't vary. Maybe it's just the number of fish in the tank, and we're doing that, and then we're measuring something else. And the number of fish in the tank stays constant, and we assign a parameter to it. Like how much fish food we're gonna, I don't know. So yeah, so it might be varying, might not be varying, depending on if we're thinking about time going by and fish being bred, or if we're thinking about something else. But in either case, this doesn't have a symbol, so I'm not going to call it variable or parameter at this point. We'll call it neither of those because it's just a concept. Now what about, let's see, I see 6, 7, and 8 all have letters at the beginning of them, so they won't have that problem. What about number 6, H, the height of the water in the tank in feet? That's varying. I can see that it's being filled at a rate of 17.9 gallons per minute. So the height of the water in the tank must be changing. If there were a leak in the tank also, it could be changing at a rate of 0, but this would impact the height of the water. So H is something that would take on a variety of different values because of this being filled. The height of the water in the tank in feet, due to this being filled, seems to be something that's varying then. We could relate the height to the volume and the radius and the fill rate and all those sorts of things. We don't actually have the radius, but we have a symbol for it. So this is a varying quantity, and we have a symbol for it. So in this case, I'd call H a variable. So H is a variable. The height of the water in the tank is a varying quantity. What about number 7, lowercase v, the volume of the water in the tank in cubic feet? Yeah, that's something that's varying, and this lowercase v impacted same as h by this, not by the same amount, but because the tank is being filled at this rate, the height and the volume in the tank are both varying. So I'm going to say, yep, also varying, and this lowercase v is then called a variable. What about this uppercase V with a subscript n, Vn, the volume of the water in the tank at noon today? Now that'd be one specific value of lowercase v, maybe, and so it's got its own symbol here. This is not something that's varying. We're talking about one specific value at one specific time. So this symbol is called a parameter because this is a non-changing quantity. Now, if I were to change it to a different situation, say it's the volume of the water in the tank at noon yesterday, it would take on a different value for yesterday, or maybe I could have a different tank and use the symbol Vn for the volume of the water in that tank at noon today. So this symbol is a parameter because it's representing a quantity that has one value, not a whole range of values that changes from one to the other. So it's not a variable. But this symbol here represents a specific value of the volume, a specific value of lowercase v at a specific point in time, and we gave it its own symbol. So that symbol is a parameter, and this is a non-changing quantity or non-varying quantity. Now what about number 9, the tank's filling rate in gallon per minute? Is that a varying quantity or a non-varying quantity? Non-varying quantity. Now we've been assigning things like that, this rates, we've been calling them M or something. This doesn't call it anything down here. Now I know it's 17.9, according to that, that's not a mathematical constant, but if I said 17.9, the tank's filling rate in gallons per minute, I would say that that 17.9 is a constant. But this is definitely something that's non-varying. I'm not going to call this sentence a constant. I'm going to say it's a constant quantity. So we can talk about constant quantities and varying quantities, things whose values change and things who take on only one value within a situation. But then if we assign symbols to them, we can talk about them as constants or parameters or variables. So just be careful with your terminology. When you're using things, it's really easy to just kind of use variables, a catch-all, anything that's a letter, let's call it a variable because it's easy to do that. But there's actually different words for different meanings. And when we use the word variable, we want it to represent a quantity whose value is actually varying. That way the word makes sense. All right, so let's see if I can get back to, no, there we go. I'm gonna just go on to this the fast way. All right. So another quick review. And again, just representing expressions and their values. We're going to talk about what it means for something to be a function and review function notation. Just make sure we're on the same page and we think about some different ways we can use function notation. Function notation is a key to being able to express things succinctly without having to do a lot of computations. It also helps you to do some cool stuff in GC, which again, you don't have to grab a calculator and find a number for something and use the answer to you can use function notation to represent having done some computations, which is nice if you define functions. So, suppose that the distance d that a motorcycle travels from an intersection, and we're measuring that distance in miles, is a function of elapsed time. And we're measuring time in minutes. And we're measuring this all relative to since leaving the intersection. And this relationship is called G. So G is the relationship between time and distance. Distance is something that we're measuring in miles, and time is something that we're measuring in minutes. And there's a relationship between those two if you have this situation. We're riding a motorcycle through an intersection. And it doesn't say anything about constant speed or anything. We're not going to try to write a precise function for this. But if I use function notation, call the relationship G, and 8.3 is an input to this, thinking about just how we normally relate distance and time, what would maybe be the meaning of the 8.3 portion of this expression? If this, yeah, the 8.3 would be the minutes that are elapsed since you left the intersection. So this g of 8.3, even though I don't know a value for it, would mean the distance that the motorcycles traveled past the intersection in the 8.3 minutes that have elapsed since we passed it. So this g of 8.3, when you see this, we don't have to know, like, how do I calculate that for this to have a meaning? Because I don't know how fast the motorcycle is going, or if it was going the same speed or changing speeds or anything about that. All I know is g is this relationship between time and distance. And again, I just kind of describe this relationship. Said the normal way we do this would be like the independent variable, or the starting point would be know the amount of time, and then you compute a distance from that. Distance is defined by time as opposed to time being defined by distance. You can obviously invert those. But just because time does its own thing, usually time is used as an independent or input variable when we have a choice. So this expression here, g of 8.3, thinking about this, this g of 8.3 on its own, without knowing its value, means that distance, the distance that the motorcycles traveled in the 8.3 minutes since it left the intersection. So this tells you the input, it tells you the time, 8.3, but it's representing the whole expression, the distance in those 8.3 minutes. So g, the symbol in front, tells you what relationship we're talking about. In this case, not really a question because I just posed one relationship here, the distance and time, and g is the relationship between time and distance for this motorcycle, with all the units and relative to what's described in the couple sentences above. This inside the parentheses is the independent variable, which I said this time just go with it. We'll say that that's the time aspect to this. So this represents the 8.3 minutes. So we've got a dependent variable value, g of 8.3. So if I were thinking about graphing the distance that the motorcycle had traveled past the intersection, say, well, at time 0, it's at 0 miles past the intersection because it's all relative to when the way the variables are set up, the way the quantities are related. At time 0, it's 0 miles past the intersection because it's relative to that. At time 8.3, it's g of 8.3 miles past the intersection. So even though I don't know what the value of g of 8.3 is, I know that this is the dependent variable value that corresponds to, in this relationship, 8.3, the value of the independent quantity of time. So we can see this. Just make sure you realize that this tells you the pair that corresponds when you have a function, the input and output that corresponds. We don't have a number value for g of 8.3, but I can say that at 8.3 minutes past leaving the intersection, the motorcycle had driven a distance of g of 8.3 miles away, or had traveled that far from the intersection. So without knowing a number for it, I can use this symbol to represent that amount. So we're doing a lot of talk about using these symbols. So g of 8.3 then is a single value of the dependent quantity, just like 8.3 is a single value of the independent quantity, time. But time and distance are things that are varying, and these are just individual values of that variable. 8.3 comma g of 8.3 could be a xy point if we're graphing something. All right, so if I have not a description in a sentence, but just a kind of generic mathy expression, f of x equals 3x squared plus 8x minus 17, quadratic function. If I say f of 2, in this case I could find a value for f of 2, But realize that just like before, you can just use the symbol f of 2 to represent what? Well, it would represent the output from this function when x has a value of 2. So 2 comma f of 2 would be a coordinated pair of values that this function relates. This is a relationship f. That maybe it's the motorcycle, maybe it's not. But just keep in mind that f of 2 represents that output value, or the dependent variable value, where 2 was the input and the relationship name is f. So f isn't y, f is the relationship, and then f of 2 could be a y value if you want to think of it graphing on xy axes. So 2 is the input and f of 2 is the output. F is just the name of how the input and the output are related. All right, so again, we can find it, we cannot find it. Function terminology-wise, if I have two quantities represented by y and p, notice there's not a p here, suppose that p is a function of y according to this rule. So notice there's not a p listed here, and this one y would be the independent variable or the input to this function. The function relationship is called z. The relationship between y and p, apparently, is z. So I plug in values for y, I get out values of p, and z is the name of the mechanism that does that converting from y's to p's. So it doesn't have to be x's and y's all the time. But here are some terms that go along with functions. Some of them sound kind of the same as one another. So function definition. So when you're defining a function, and we're going to do this in a moment using GC, I'm going to have you define a function and then use it to do things. When you're defining a function, you have to state a rule, including what's the name of the function, what's the input, and how do I compute it. That function definition is that whole z of y equals 3y squared plus 8y minus 17. So that whole expression up there defines function z by telling us what's the input, although input variables are kind of placeholders. It's waiting for a number to be plugged in. So it doesn't really matter if I call this z of y or z of q or z of whatever. It would have the same relationship between two things. The dependent variable we're not going to get from the function definition. That would have to be given someplace else. In this case, it's up in the sentence above. The dependent variable would be p in this situation. So two quantities are represented by y and p. P is a function of y, and it's given by using this relationship z. So the dependent variable in this situation is apparently called p. Sometimes you might see, like you've probably seen written like y equals f of x. Y is the dependent variable, f is the function, x is the independent variable, but f is the function relationship. Y is the output from using f of x. In this case, p is the output or the result from using z on our input y, using z of y. What about our independent variable here then? That was maybe the easy one. Yeah, independent variable here is just y. The way that this is structured, this is set up so the independent or the input is y, values of this variable that can go into those spots. The function name is z, yeah. Function rule and function definition are pretty close to one another. Usually what's meant by function rule is just the computation part, like the right-hand side. So the function rule is, and it's the how do you do it part. The value of p, no, that looks a little strange. The value of p, well, z of y gives me any value of p that I want for different values of y. But again, the value of p depends on what value of y I use. And so z of y is a quick way to write a general value of p. Z of something, z of 2, z of 19, those would all give me individual values of p, depending on which input I'm looking for them corresponded to. So just keep in mind that when you use function notation, you usually only see the independent variable as a part of that, and the dependent variable is someplace else. It's listed or known, or sometimes you have to make up a symbol for it. Sometimes the dependent quantity is described and there's not a variable given. If you want to assign a variable to it, you may get to do that yourself. All right, so what I want to do is take a look at GC. I'm going to open up a file that I have. I'm going to post this. Let's see. I wonder if I can. I think I have this posted on Canvas already. I just have to make it available to you. That would be faster. I have the box problem in here. Car sync. Let's see. There's lots of stuff in here. Nah. All right. So I'm gonna open this up and we'll go through this together. I'm gonna post this for you to play around with later. This is GC. You probably haven't had too much of a chance to play around with it. I know in recitation on Friday you'll probably talk a little bit about it, especially if you're having difficulty getting it downloaded. But let's see if I can get this zoomed properly. There we go. All right, so this is a GC file, and often in class I will post a GC file for you to open up and we'll work on some stuff together. One of the things that you can do in it, notice there's like some text and writing, just like with, if you've done computer programming ever, you can have your programming lines and you can have your comments and stuff. Well, this gives you lots of ways to write in comments, so you can write descriptions, but I can also use it for class purposes to give instructions. So on this one, this is just one that I've opened up here, and I'll show you when you can play along, and I'll show you how to do so. But so the cost of materials in dollars for a certain rectangular box with base dimensions L feet and W feet is given by this. So this expression right here is just a formula. It's not a function because I don't have a dependent variable. It just says cost equals 4LW plus 288 over L plus 96 over W, wherever that came from, probably simplified from the cost of the materials on different sides of this and whatnot. So if I look at this with respect to various boxes here, there, I get that right on the top of the screen. 4LW plus 288 over L plus 96 over W. Look at this big messy expression here. See if you can decipher based on the sizes of box type number 1, type number 2, and type number 3, what on earth this computation line, which spans 2 lines, is doing. Look at the cost formula, look at the box measurements. See if you can see what that big ugly expression is. Yeah, total cost of, one of each of the 3 boxes. So 4LW plus 288 over L and 96 over W. So this has 8s and 4s in place of L's and W's. This one is the same but 2.6s and 5.9s. And this is the same but 10s and 7.25s. Would you agree that that's kind of tedious if you needed to, if I said, oh, find the cost of making one of each type of box, and you have to do all this computation, whether it's in GC or on a standard calculator or just by hand or wherever you wanted to do this, a little bit tedious, yes? So just thinking about function notation, if I want to use this ugly function over and over but use it the same way, whenever there's something repetitive to be done, there's probably a good way to have computers do this more efficiently than doing it the long way, by actually typing out the same thing over and over again. So this cost, now this is a function where there are 2 different input variables. L's and W's are things that can, well, we'll be putting in specific values of L and W. If I let either one vary, the cost varies. These are just 3 specific box sizes. But the cost depends on both L and W, agreed? So I'm going to put this in right here because I don't want to scoot this down. Let's see. Can I do it there? It won't let me. There we go. So suppose that instead of doing this computation the hard way, looking at this cost function, what I can do is I can define a cost function and then represent the costs of these various types using function notation. Now this is a fancy sort of function. I can call it whatever I want. Let me call it function f. If I want to call f a function and I want to define it, one thing in GC, there's 2 different sorts of parentheses. Typically when you write parentheses in GC, it just says, oh, multiplication. You know, if I have 4 parentheses x, it's 4x, it's multiplication. If I want it to be parentheses for function notation purposes, you have to hit Control 9. So like Shift 9 is where the left parenthesis is. By the way, in GC, when you hit 1 parenthesis, it gives you a pair. You don't have to type the closing parentheses are already there. I'm going to hit Control 9, so Control instead of Shift, and then where the parenthesis is. And this squishes it right next to the F or whatever symbol I had, and it's saying, ah, you're defining a function. So my F, I want it to be a function of L and W, because, well, it'll make it easiest. This is going to be my cost function. I want to finish the definition. All I'm going to do is write out exactly what it says up there. Oh, this cost function here, f of L comma W, it's a 2-input sort of function, so a little bit fancy. But it's 4LW, and you just like when you're writing math, you don't have to write times signs between variables and numbers, plus 288 over L, although when you're in a math line, it will make it look like a fraction, and then plus 96 over W. So if you type this in, it won't do anything. It doesn't graph it. It doesn't give you anything. This is just defining a function. That's all that this line does. And if you hit Command Enter, or let's see, what is it on PC? I think Control Enter, it'll get you another command line. They just kind of alternate through a bunch of colors. If you don't like them to be different colors, you can change them all to the same color. Clicking on this box, it's useful if you're trying to graph something. Changing the color of that box changes the color of the curve that gets graphed. If you're just writing stuff and doing computations, it doesn't do anything other than sit there, so you can color code them to be like, oh, these are all the blue ones. That was problem number 1. But if I wanted to find the cost of one of each of these boxes, now that I have function f defined, I can refer to function f, again, just using math notation, f of, so I'm going to do Control 9 to get my function parentheses. If I want the cost of box 1, that's a 8 by 4 length and width, so I'm going to do 8 comma 4. And it tells me the cost right there is $188 for box number 1 without having to put in the 8 and the 4 into the formula. If I want a cost of one of each box, I'd say, oh, plus f of 2.6 comma 5.9. And then I just use the right arrow to get out of those parentheses. Since when you type parentheses, it automatically gives you both halves. If you want to get out of them, just arrow to the right, or you can click to the right. And so you can do these with any sizes, but just to repeat the expression that was there previously, 10 comma 7.25. So this result I can get using function notation. If I define a function, I can do the computations in it pretty easily. There's one weird thing that, well, it's not weird, it's just unfortunate about GC that they can't unfortunately do. You can't copy text and paste it into a function line and have it translate it from, like I can't copy that cost formula, the right-hand side, and paste it into a command line and make it usable math, I actually have to retype it. But if you did want to reuse anything else, like if I want to reuse this, I can copy and paste this expression to do something else with it. So if I want to know what's the cost of 10 boxes of type 3, and say, oh, well, it's 10 times this. Like, so if it was something annoying to type, you don't have to type it again. But in any case then, I just wanted to give you a little preview of, again, a little bit more with function notation and a little more with GC. So you can see some of the things that you can do with it. We're going to use it for a lot of things. Next Tuesday in class, we're going to have a whole activity that we do with this. Make sure you bring your computer to play along. But I will post this file that I had that I used today. I'll post that on Canvas so you can kind of play around with it. They're just files. If you have GC on your computer, you can just click on it, download it, use it, play around with it, see what happens. All right. I will see you next week. Make sure you remember you have assignments 0, 1, and 2 due before the next time I see you in here.
I like your shirt.
Thank you.
Oh, so when I'll recognize your face, and I'll be like, I know that face, and then I will never remember your name. This one.
Tomorrow, yesterday when I did my homework, I found a question about this. So about this question.
Okay.
So it said that how many years it would take. So when I use this, it tells me that 1 year equals to this. But when I did this question, I should use 365. So I want to know. So I wonder if I have this kind of question in test, so I should.
It would clarify. Yeah. Yeah. Yeah.
Okay, thank you.
Yeah. That's one of those things. Depends. Yeah.
And I wonder how to download GC.
Let's see. So from the announcements, there should be a link to it. In this, yeah. It's also in the book, I think, but go to section. Oh yeah. So yeah, that just does take you to the book. So it's in section 1.0. It says. So scroll to 1.0. Install graphing calculator.
Oh yeah. So just.
So here's the Mac version. Here's the Windows version. So you want.
Alright, I got that.
Yeah.
Yeah, and the final is about how can I open it? So
oh, you have to have the program first.
Program first.
Yeah. So this is this .gcf.
Yeah.
That's graphing calculator file. So you have to have that program installed first.
Alright. Thanks.
All right. Yes.
What were the later class times that you said that you had?
I don't have any other class times. It's another instructor, and it's Tuesday, Thursday, like at 1, I think, 1:15, something like that.
Okay, I'll have to look.
Okay.
I'm gonna have to change something with my schedule to get maybe it's one out there.
All right, we'll figure it out.